In this video, we are going to look at the graph of tan of x. So as per usual, we're going to fold out the unit circle. Of course, here we have 0. Here we'll have pi over 2. We'll have pi here, 3 pi over 2. And this will be a complete revolution, so we can also call this 2 pi. Now, we're going to also need our coordinates. So if you recall, this is going to be 1, 0. Here we're going to have 0, 1. Here we're going to have negative 1, 0. And here we're going to have 0, negative 1. Now, if you recall, when we looked at the basics of our unit circle, we highlighted that here we will have our coordinate point corresponding to cosine theta and sine theta. Now, what's going to be important when we're graphing tan, we need to recall that tan is, right, tan of x is actually sine x divided by cosine x. And we saw that when we looked at the unit circle. Now, this is going to be important when we're graphing, right? When we're folding out the unit circle. So for instance, let's say we're using the points that we used before. So let's say we're using this pi over 2, pi, 3 pi over 2, and 2 pi. Okay, so when we are at 0, right, notice what's happening here. We have sine, so let's say we're at 0, right, 0 radians. Well, sine x over cosine x, well, that's going to be, so my sine is 0 divided by my cosine is 1. So at 0, I'm going to be at 0, okay? Now, when we're at pi over 2, so you do this if you're trying to figure out what it's going to look like, right? So when we're at pi over 2, we're still doing sine over cosine. But at pi over 2, notice sine is 1 and cosine is 0. But recall, here we cannot what? We cannot divide by 0. So here it's undefined. In other words, we're going to say we have an asymptote. And so if you're familiar, an asymptote is a point or a where your graph does not touch. So in other words, the graph will not touch anywhere for the line y equals or x equals pi over 2. Now, in this instance, we have an asymptote here. We use a red line to represent that. So it means that this tan graph will not touch that line. Now, we can go a little bit step further. So let's keep going to see, well, what we're going to get for when we get to pi. Okay, so when we get to pi, what happens? Well, we have what? Uh-oh, not that. When we get to 0, this is what we're going to have. I'm sorry, when we get to pi, this is what we're going to have. And so my sine is 0 and my cosine is negative 1. So we are going to be at 0 again, right? Now, we can keep doing this. And what you're going to notice here, so if you go back to 3 pi, so if we go back to 3 pi over 2, okay, what we're going to get, and that's going to be here. So sine is negative 1 divided by, again, 0, right? But we know we cannot divide by 0. So in other words, we have another, so this is undefined. So we have another vertical asymptote here. So what happens here is we're essentially going to have a vertical asymptote everywhere we have an increment of pi over 2, or everywhere cosine is 0, right? Likewise, if we were to go in the opposite direction, this would be negative pi over 2. This would be negative pi, negative 3 pi over 2, and this would be negative 2 pi. Right? And so we're going to still have a vertical asymptote at pi over 2, negative pi over 2 rather, as well as negative 3 pi over 2. So when we find that we're graphing tan, cotangent, cosecant, and secant, there's going to be a very important aspect of our graph, which is our asymptote. So that's going to be an introduced new aspect of our graph when we're graphing it. Now, of course, we cannot fill these in just looking at the unit circle. We cannot fill the points in. All we know is that the graph is supposed to go through these points in increments of pi, right? But if you were to fill this in, now remember, even though we're at 0, we have other values that are on the unit circle. Of course, we highlight a few. We highlight pi over 6, pi over 4, and those things, but there are other values on the unit circle. So if we were to fill this in, so for instance, let's say we wanted to do, let x be equal to, let's say x is 1.3, right? So 1.3, and you can like literally put this in your calculator. And so you'll find that we'll have to also do this when we're doing examples for graphing tan, right? So if you look at pi over 2, remember pi is 3.14, okay? And if you want to look at the numerical value for pi over 2, you can literally put pi divided by 2 on your calculator. And so you will see that this is actually about 1.5, right? Alrighty, so I'm going to find a point that's a little bit below that. So let's say 1.3. So if you plug tan of 1.3, you will get the x value that's associated with that. And so you would get around 3.6. Okay, so you literally plug this in your calculator. All right, and so that will put us about, let's see, about somewhere here, right? And then you can actually fill some more values in. And so also if we wanted to do a negative of that, we'll have, if we have x equals negative 1.3, then tan of negative 1.3 is going to give us negative 3.6. So we'll be about down here somewhere. So if we wanted to really graph tan, it will look something like this, right? It will tend towards the asymptotes, but it will never touch the asymptotes. And if we were to continue this pattern, in fact, this is what the graph of tan would look like, right? This is the graph of tan. Now, like I said before, there are some things that are going to be a little bit different when it comes to the graph of tan, right? And so let's kind of look at the different characteristics we saw before when we were doing the sine and cosine graph. So before, if you recall, we looked at a few features of the sine and cosine graph, right? We looked at the amplitude and those type of things, but those things are not going to be in play here. For instance, amplitude is not going to be in play here for your tan graph. Instead, right, we are going to have, so this is your basic graph of tan x. So now let's look at if we had a graph of y equals a times tan bx minus c plus d. So that a that used to be, that absolute value of a that used to be our amplitude for our sine and cosine graph, this is now the stretch factor for our tan graph. Now, if you notice the period, the period is not between 0 and 2 pi anymore. In fact, if you notice, the period is like half of that, which is pi. So the typical period, if I may just kind of break this down a little bit for you, the period of this graph is going to be just pi. Okay, it's pi. You still have your stretch factor. Your stretch factor is still the absolute value of a. And this is just for your basic y equals tan x graph. Okay. So yes. And then, of course, what's still going to be in play here is, for instance, like your domain and your range and those type of things. So if you look at this, your domain is not going to be any value you can think of, because there are going to be some values that you have asymptotes. So wherever cosine x is 0, we're going to have asymptotes. Okay, and so let's kind of look at the more general form. So this is your standard y equals 10x. So let's kind of look at the more general form. Now, let's say you have a general form y equals a tan bx minus c plus d. The period of that graph, if you want to identify what the period is, it's going to be pi divided by the absolute value of b. Now, our asymptotes are going to be wherever cosine is 0, right? We saw that previously. So now, when we look at the cosine, the asymptotes here, so the asymptotes are going to be equal to wherever x is. So it's going to be starting with your phase shift, and we'll look at what the phase shift is. So that's not it. Or it's just pi over 2 times the absolute value of b plus pi divided by the absolute value of b times k. Now, if you think about it, I'll look at it a little bit more, but why we say times k is because when we go around the circle, there's a pattern here, right? Cosine is 0 at these increments. And so that's why we're looking at where k is an integer. But we'll look at this a little bit more in depth. Your phase shift, not absolutely important, meaning this is going to be your horizontal shift, if you remember. And so your phase shift is still going to be that c over b. And then we'll still have a vertical shift, but it's not a line. Remember previously that d represented y equals d would be your midline for your sine and cosine, but instead here, d is going to represent your vertical shift. Okay, let's look at a quick example of how we can graph a tan function. Let's say we are tasked with graphing y equals -2 tan of pi x plus pi minus 1. Now, as done previously, I always like to say, let's identify, well, what are all of these things that we have, right? What's your A? What's your B, C, and your D? Okay, so A is going to be -2. So A is -2. Our B, what's that going to be? Well, B is going to be pi. Now C, if you recall, the actual formula, it calls for, right, bx minus c. So C calls for a negative in that value, but in this instance, we're going to have a plus here. So my C is actually -pi. And then my D is going to be -1. So these things are going to help us now to come up with our graph. So for instance, our stretch factor, right? Our stretch factor, that's going to be the absolute value of -2, right? Or the absolute value of A, which is going to be 2. Then if we want to look at our period for this graph, well, our period, well, that's going to be pi over the absolute value of B, right? And so that's going to be for us pi over 2. Okay, that's going to be your period, pi over 2. Oh, nope. B is not 2. B is pi. So it's going to be pi over pi. And that's going to be 1. There we go. Now let's look at the phase shift. So the phase shift. Okay, well, that's going to be still C over B. Right, C over the absolute value of B, or just C over B rather, right? C over B. And so that's going to be equal to, right now, C is negative pi divided by B, which is pi. So our phase shift is -1. Okay. Now, lastly, we're going to look at our asymptotes. And this is going to be very important when we're graphing our sine or tan function. So we're looking at where are the asymptotes. Okay. So to find the asymptotes, recall that we would do, well, we could use this formula here. But sometimes the asymptotes, they're affected by your phase shift. So we can also utilize C divided by B plus pi divided by 2BK, right? Because your phase shift is going to have an effect on your asymptote. Well, we can actually fill these in to find where the asymptotes are going to be. Remember, K is an integer, meaning a number, 1, 2, 3, -1, -2, and so forth. So we already know what our phase shift is. So we know C over B is -1. Pi plus pi divided by 2 times B, which is pi. Okay, and this is times some integer K. So let me erase the absolute value here. It shouldn't be there. Okay. So if I simplify this a little bit, you can get rid of the pi's. So this would be -1, right? -1 plus 1/2 times K, where K is an integer. So now let's kind of dive in a little bit more, right? Just dive in a little bit more to identify our asymptotes. So if K, let's say K is equal to 1, right? If K is equal to 1, what happens here? Well, we have an asymptote at -1 plus 1/2, right? And if we recall how to do this, you can put this over 1 here, and then you would try to get equal denominators. So you'll be times 2 over 2, right? So we'll have what? -2 over 2 plus 1/2. And so that will give us what? A -1 over 2. Okay. All right. So we have an asymptote at -1/2. Okay. Now, what if K, so you really can play around with this. So this is if K is 1. Let's say K is -1, because you can either do positive or negative values. So let's let K be -1. So then this implies, or we'll have here, -1 plus 1/2 times -1. So just wanted to highlight here and putting in that k here, right? So for instance, here I plugged in 1 for k. Okay, and that's from this formula here, right? All right, so if k is -1, then this becomes -1 minus 1/2. All right, so this is -1 minus 1/2. Still do the same thing, so this becomes -2/2 minus 1/2. So we'll have here -3/2. All right, so we can now start graphing. We have some information and we can like put these different characteristics on our graph. So if I were to graph this, or a cycle, sometimes they'll say, oh, it says graph 1 period, so perfect. I know there's an asymptote at 1/2, so, or -1/2, so I'll say this is -0.5, right? And then -3/2 is roughly -1.5. Okay, so this is telling me here that I have vertical asymptotes here. So I'm going to graph those. I always like to graph my asymptotes first because now I see where my graph should be. Now let's look at the shifts. We see here that we have a phase shift of -1. Right? So that means, recall that the graph started where? Where did the graph start? I always like to look at where the graph started. It started at 0, right? That's where we started. So if we have a phase shift of -1, we're going to the left 1 unit, okay? So we're going to go over to the left 1 unit. So instead of being at 0, I'm going to be here at -1. But I can't only do that because I also see that there is also a vertical shift. Remember, a vertical shift. D is my vertical shift. So I went down 1 unit. So let's say this is -1. So that means that I'm going to have a point here. So instead of my point that was on 0, I shift over to the left 1 and then I shift down 1 unit. So that's where my 0 is going to be. Okay. Now you may want to see, well, I don't know what this graph should look like. Well, we know the original tan graph looks something like this. So one thing I can note here, if you recall in the previous sine and cosine videos that we did, if we have a negative sign, well, this graph is going to flip. Remember, it's going to flip. So since we have a -2, the graph is not going to look like its regular graph. Instead, it's going to be flipped. And so now it's going to look something like this, right? But if you're not absolutely sure, we can actually plug values in. So remember I said, well, sometimes you're going to have to plug values in to kind of see where to fill your lines in. And so I'm going to plug values that may be on this side of the graph and that's on this side. You can do 3 values. I like to just do 2. So first, let's look at -1 point. So let's say x is 1.25, or -1.25. So if x is equal to -1.25, then we know that y is going to be equal to -2 times tan of pi x, which is what we just said is -1.25, right? plus pi. Negative 1.25 plus pi. So you can literally plug this into your calculator. Minus 1. And so if you plug this into your calculator, you'll see that here you will get that y is equal to 1, positive 1. So we're at negative 1.25, y is going to be positive 1. So it's going to be something like this, right? Not quite. It's going to be here. Oops. About here. There we go. And we can do the same if we were to pick a value on this side here. So if we were to let x be negative 0.75, let me give a little bit of a space up here. Oh, not that. Okay, so if we let x be equal to negative 0.75, then that means y is equal to what? Negative 2 times tan of pi times 0.75, well, negative, plus pi plus 1 minus 1. And again, you can plug that into your calculator and you will get that y is equal to negative 3. Make sure if you're using your calculator, make sure your calculator is in radians. Okay, so this would be negative 3. Okay, so it will be here. So this also further confirms the shape of the graph, right? So the graph would tend to something like this. Let me, I'm not the best at drawing graphs. So, nope. One more time. Maybe if I start here. Something like that, okay? Yes. But at any rate, you get the drift here. This is how you would graph your tan function.